Welcome again, students, to this online class. So today I want to look at asymptotes. I want to talk about asymptotes. And specifically, we would like to look at three of them, which is the vertical asymptote, which we have already met. You have already met, and we have notes on this one. You can go past as brief as possible. So the second one we would like to look at is the oblique asymptote, or some people call it slant asymptote. So this one is the one that we'll spend a little bit of time on this one. And the last one, which we'll just deduce from the slant or oblique, will be horizontal asymptote. So we'll deduce that straight from the slant asymptote. You'll see how we'll do that. Probably that will always be true for all the rational functions. So, but asymptote can be very complex, but let's make it as simple as possible. So let's go straight to the first one, vertical asymptote. And straight away, let's start with the definition. What does it mean to say we have the vertical asymptote? Previously, we have seen that the line x, which is equal to a, is called a vertical asymptote of a function y, which is equal to f of x, if one of the following is true: the limit of f of x as x goes to approach a from the left, if the limit is, it could be plus or minus infinity, or if when you try to approach a from the right, and then you find that the limit of f of x is still plus or minus infinity, then each of these cases will give us a vertical asymptote at x, which is equal to a. So this is what we have now, and we had a lot of example previously. Remember, we look at functions like a tangent theta, where we got a number of vertical asymptote when cosine was 0, because tan can be written as sine over cosine. So for the vertical asymptote, I just want to leave it right here, just right here. Let's get to the second one, which I think we'll spend a little bit of time on, which is the oblique or slant asymptote. So, what is the oblique or slant asymptote? So we can say the straight line line y, which is equal to kx plus b, is oblique. So we can call it oblique or slant asymptote. It becomes oblique or slant asymptote of y, which is equal to f of x, or the function f of x. In this case, we'll pick one case of f of x if the limit of x as x goes to plus infinity, the limit of f of this function as x goes to plus infinity, that's the limit of f of x minus the straight line, which is kx plus b. If that limit is 0, then we'll conclude that the oblique, we have the oblique asymptote. That's one thing which is still a little bit tricky at this stage. So let's go a little bit inside and then try to get into the details of what we are talking about. In fact, let's first demonstrate. Suppose you have your graph here. What are we saying about this? So we are saying, suppose you have some kind of a straight line here, and then you also have your graph here, f of x, and then find that as you go to positive infinity, f of x come as close as possible to your line, your straight line. So you can see here we have a straight line which is y, which is equal to kx plus b, and then we have f of x here, and you can see as x goes to infinity, the behavior of the function now comes as close as possible to y, which is equal to kx plus b. So that's the slant asymptote. And the same thing can be said about as x goes to negative infinity. We can still get a slant asymptote. So we need to make note of that, because we are going to stick with positive infinity just to drive the concept. But the same argument can be made as x goes to minus infinity. So let's note that first. Let's note that. So similarly, we introduce oblique asymptote, as x goes to minus infinity. So, but now to get a complete clue of what are we talking about when we talk about an oblique asymptote, at this stage we are still talking a little bit of a hard language. But now let's introduce a theorem here which will lead us to an example. So theorem. So what does the theorem say? So here is the theorem. We say a straight line y, which is equal to kx plus b, is an oblique asymptote of a function y, which is equal to f of x as x goes to plus infinity. Remember, the same can be argued with as x goes to minus infinity. If and only if the following: if and only if the following two limits exist and are finite. So what limits are we talking about here? What limits are we talking about here? So we are talking about the limit as x goes to plus infinity of f of x over x to be equals to k, and the limit of this function as x goes to plus infinity, the function is f of x minus kx is equal to b. And these two conditions, so the first one is the limit of f of x when divided by x, it should give us the constant k as x goes to plus infinity. And also we have another condition here, that's the limit as f of x minus kx goes to b, as x goes to plus infinity, the limit of this function should be going to b. And remember, what is our k? K is the slope of the oblique asymptote. And it tells you that we can even use this theorem to kind of calculate the value of k. And also remember that b is the y-intercept of the straight line, or our oblique asymptote. So we can use this part of the theorem to calculate b. That means where the straight line or the oblique asymptote intersect the y-intercept. One thing which you should put into mind. And that's exactly what I'm going to use in the following example. So, having said that, let me say this. This one is your job if you like, but in this course we are not going to give a proof of this theorem, but you can do it as an exercise to just exercise your muscle. We'll not even ask you about it. So the proof of this part is left as an exercise. So you can practice with that, but we'll not even ask you about it. So let's go to the example. Now look at how to find the oblique asymptote using this theorem, or two methods actually. So the question says find the asymptotes. So it asks you to find the asymptotes to the curve y, which is equal to x squared plus 2x minus 1 divided by x. So you have this curve or a function that you want to find the asymptotes on this function. And remember, the question is a little bit more general. So it's better to try to find all the possible asymptotes here. So the easier one to find straight away is the vertical. So we can try to get the vertical asymptote. We can see straight away that if we try to take the limit as x goes to, especially because we are dividing by x here, so we know that at x which is equal to 0 we'll have a problem there. So the function will not be defined. So as x goes to 0 from the left, we can see that our function goes to infinity. And if we try again, if as we approach 0 from the right, you'll do the test, you will find that your function approaches minus infinity. Therefore, we can say x, which is equal to 0, is the vertical asymptote. Good news. So that's the first vertical asymptote that we get. And the thing is, here we have only one vertical asymptote, but that is not a problem. So let's try and look for the other asymptote. Now let's use that theorem that we find. So next find the oblique asymptote. Next, find the oblique asymptote. So let's try to use the theorem that we had. So remember we need to find the k first. We say we can find k by saying the limit as x goes to infinity of f of x over x, which in this case will be the limit as x goes to infinity of y over x, and you remember how our y is given in this case. So as x goes to infinity, therefore we have, if we divide that function by x, we are left with x squared plus 2x minus 1 over x squared. Remember, we had x only in the denominator. So if we divide by x, now we have x squared. And here is another technique that we'll use most of the time, especially when we are dealing with infinity, the limit as we approach infinity. So most of the time we'll try to factor x squared in this case, or the highest degree, the highest variable here, the variable with the highest degree. So we have x squared, which is the highest. Otherwise we have x to the power 1, x to the power 0 on the numerator. And in the denominator we have only x squared. So we'll try to factor x squared out. Then when you do that, and then the x squared will cancel with the x squared in the denominator. So you're left with nothing but 1 plus 1 over x minus 1 over x squared. So this is the technique we'll use, and it makes you to see clearly what you get as x goes to infinity. So if now you apply infinity, you can see this term goes to 0, you are dividing by a large number, this one goes to 0, you are left with just 1. Good news. And that means our slope in this case is nothing but k, the slope of the oblique asymptote. We are almost there. This is good news. Now let's get the y-intercept, the b. So for the b, we know that b will be equal to the limit as x goes to infinity of f of x minus kx. If we plug what we have there as x goes to infinity, you will find that we have here x squared plus 2x minus 1 all over x. Remember, we are not dividing by x this time, but we have to subtract kx. Remember, we found k to be 1, so it will be just x here. Interesting. You can put them on the same denominator and you'll find that x squared will be cancelled. So once it is cancelled, we are right here where we have the limit as x goes to infinity of 2 minus 1 over x. So we have already somehow tried to manipulate by dividing by x, by factoring x outside such that it cancelled. Then this results with nothing but the value of 2. That means we are ready now to write our oblique asymptote. So now we can say therefore y, which is equal to, remember the slope was 1, so it will be just x plus the intercept, y-intercept, which is just 2, is the slant asymptote or the oblique asymptote. So this is one way of going about the oblique asymptote. The second method which you can use, you can use, let's look at method 2, which I will not go into too much details, especially for this function. So what can you use for method 2? So with method 2, you can perform some division. In this case, we have x squared plus 2x minus 1 over x. So you can do long division. But in this case, we have a simple expression. If we have a complicated expression, you can still do a long division or synthetic division. So once you do the division, you should get x plus 2. That means we are dividing the first 2 terms by 2, but you will get the remainder 1, which still need to be, remainder minus 1, which still need to be divided by x. And then after that division, this is your slant asymptote straight away. So this portion represent your slant asymptote. This is a simple procedure that we normally use. We normally start with a bit difficult method, and then later we introduce the simpler one. So this is a simpler way to get your slant asymptote. That's it. That's it with the slant asymptote. So now we are kind of ready. Remember, we have worked with positive infinity, and we also make an argument that you can do the same with minus infinity. That's what we agreed you can do. So now let's come to the last asymptote. I'm stopping here with the oblique. So the last asymptote is horizontal asymptote. Asymptote. So remember, with the oblique we had a function of y which is equal to kx plus b, which was a straight line. So now we can treat the horizontal asymptote as a special case of the oblique asymptote, where k is equal to 0. So once k is equal to 0 on a slant asymptote, then now we get an oblique or slant asymptote. If we have a rational function, is completely impossible to get both horizontal and a slant at the same time. So we will not have a slant with just a rational function. Probably if we define a piecewise function in a very complicated way, you might have both of them. But with the rational function, what we are doing here agrees. So with the rational function, we can say in particular, if k is equal to 0 on a slant asymptote, we obtain y which is equal to just b. And this is our horizontal asymptote. This is our horizontal asymptote. Let's get a little bit into it and see. So this is our horizontal asymptote, but now let's present it in the form of a definition so that you can see it's exactly the special case of the oblique asymptote in this case. So let's say definition of the horizontal asymptote. A straight line y which is equal to b, which we obtained previously, is horizontal asymptote of the function y which is equal to f of x if and only if the following: limits exist and are finite. They exist and they are finite. There we go. What are the limits that we are talking about? What limits are we talking about for horizontal asymptote? We are talking about the limit as x goes to plus infinity of f of x being equals to b. Or you can still have the limit as x goes to plus infinity of f of x, minus infinity. I was talking about minus infinity in this case. So the limit as x goes to minus infinity of f of x is equal to b. Once we have one of these cases, suppose you have your xy plane, and then suppose this is your b here. So you have this line y which is equal to b, and then the behavior of the function, you'll find that it will be somehow getting closer and closer. That means as we go to minus infinity, b gets as close as possible to the line y which is equal to b. Also on the right, it could have the similar behavior. As the values of x goes to plus infinity, the value of the function gets as close as possible to b. Close as possible, but not exactly on b. So it approaches b. So this is how you look at it graphically. Yeah, I think this was quite a long lesson. So before I stop, let me list a few things. A few things of importance before I stop this lecture. So let's say let f be somehow the, let's say, the reduced. That means it's simplified. You can't simplify any further. Reduced rational reduced rational function. Which we somehow define it to be q of x over p of x. In fact, let's go a little bit further to try to give how it looks like. So you have some function like that, and then you have plus or minus. This is a polynomial. You can see just a polynomial, the top part. So it's a rational function. It's polynomial over polynomial until you get to a0. Those are your coefficients. And then we have another polynomial in the denominator, x to the m plus many other terms here until you get to b1x, and then you get to b0. So it's our rational, the normal rational polynomial. What can we deduce from this? What can we deduce once we have that? Okay. So, number one, the graph of y, which is equal to f of x, this is what we know, will have vertical asymptote, vertical asymptotes at those values of x where the polynomial we are dividing with is 0. That means where p of x is equal to 0. We know if we can solve all the values of x where p of x is 0, we'll get all the vertical asymptote. Number two, we want to talk about slant or probably horizontal asymptote. from our argument, remember we said for rational polynomials, they cannot exist at the same time. So you either get one or none. Asymptotes. So, number A, what do you see? If the polynomial in the denominator is bigger than, the degree of the polynomial in the denominator is bigger than the degree of the polynomial in the numerator, then we know if we take a limit, we'll get our horizontal asymptote to be nothing but 0. Then the horizontal asymptote is y, which is equal to 0. So it means the limit of the rational function goes to 0 as x goes to plus or minus infinity. So in this case, your horizontal asymptote is nothing but the x-axis. So we can say it's nothing but the x-axis. What about another case? So, what about another case? You can have case number B on the slide. If the two polynomials, the top and the bottom, are of the same degree, that means m is the same as n, then we know that the horizontal asymptote is given by nothing. You just divide the coefficients of the terms with on the highest degree. That means the x to the power n. So you end up with nothing but the horizontal asymptote becomes a to the power an over bm. Yeah, that's what we have. So, what about the last case? There is a last case. Number C. Now, if if m is now, that means the degree of the polynomial in the denominator is smaller than the degree of the polynomial in the numerator. Then, in this case, there are a lot of possibilities. The first possibility that can come is the oblique asymptote. When the difference between the degree is just 1, that means the top, if it's 7, the bottom should be just 6, the degree. So, but one thing we are sure is that the graph of y, which is equal to f of x, has no horizontal asymptote. What may exist is the oblique asymptote. So that's what we know that it's not there. So, and this may say to us that there is a possibility that the oblique asymptote may exist. So, which calls for the possibility of the oblique asymptote. You can now test the oblique asymptote, and you can see easily if the oblique is there. If the difference between the degree is 1, we know the oblique will exist because we are looking for a straight line, especially for this rational function. Remember, now we have been talking about rational function. Everything can change if we go to piecewise function or some other form of the function. So our argument has been based mostly on rational functions that we are dealing with. So that's the point that you have to bear in mind as we work through these examples. But now, before I stop with all this, let me give you an exercise to work on to show that actually to find the asymptote may be a complex problem. So here is the exercise to test your muscle and many others in the tutorial and the books. So what do I want? I want you to find the oblique asymptote or asymptotes to the curve y, which is equal to the square root of x squared minus 1 plus 2. That's it. Find the oblique asymptote to this curve. I suspect it's there, so please find it. So we're interested in this curve. So now, as I stop on this part, what did we learn today? We learned vertical asymptote. We went into oblique asymptote. And from oblique asymptote, we could use the horizontal asymptote as a special case of the oblique asymptote. But we noted that this could be complex if you redefine your function in terms of piecewise or in another form. So note that. We also noted some points that depending on the rational function that we have, it could be easy to deduce if we have vertical asymptote by looking at the denominator, or if we have oblique asymptote by checking the difference between the degree of the two polynomials. We said if the difference is 1 and is 1 in such a way that the higher degree is the numerator, then we know that the oblique will exist. But we know that if the degree of the numerator is less than those of the denominator, we know that horizontal asymptote exists and is y, which is equal to 0. So those are some of the things that we learn. You can have other functions that we have if we try to use some synthetic or long division to divide, because we can have a functions which differ by a degree of 2 or more. So in that case, it means we can't talk about oblique asymptote. That's why we said the oblique asymptote that we are talking about here is restricted to the degree where we have the difference between the two rational functions, the two polynomials on a rational functions, being the degree of those two polynomials, the difference of the degree of those two polynomials being just 1. And we assume that the top polynomial has the higher degree than the bottom. So that's it. So with this, you are ready to tackle all the problems in the tutorial. You should be able to finish the whole tutorial, and you should be waiting for the next tutorial. So, and we'll continue working on the same tutorial this week. This Friday we'll continue working on this tutorial. So keep going through it and then work as many problems as possible. Good luck.